Okay, so we get hydrogen 1 and 2, helium 3 and 4, lithium 6 and 7, beryllium 9, boron 10 and 11, carbon 12 and 13, nitrogen 14 and 15, oxygen 16, 17 and 18, fluorine 19, neon 20, 21, 22, sodium 23, magnesium 24, 25, and 26, aluminum 27, silicon 28, 29, and 30, phosphorus 31, sulfur 32, 33, 34, and 36. And then chlorine 35 and 37, right? This is what you got next. Let's see here. Okay. Chlorine 35 and 37, argon 36, 38, 40. Potassium 39, 40, 1.24 billion years. Ooh. Yeah, that's the one we talk about in bananas. Potassium 41, calcium 40, 42, 43, 44, 46, calcium 48, 64 billion years. Scadium 45, titanium 46, 47, 48, 49, 50, vanadium 50, 271 million billion years, vanadium 51. Chromium, sorry for the pause. Chromium 50, 52, 53, 54, manganese 55, iron 54, 56, 57, 58, cobalt 59, nickel 58, 60, 62, 61, 62, 64. Yeah, yeah. Copper 63 and 65. Zinc 64, 66, 67, 68, 70, gallium 69, 71, germanium 70, 72, 73, 74, germanium 76, 1.78 thousand billion years. Damn. Arsenic 75, selenium 74, selenium 76, 77, 78, 80, selenium 82, 87.6 billion years, bromine 79 and 81, krypton 78, 9.2 thousand billion years, krypton 80, 82, 83, 84, 86, rubidium 85 and 87, 49.2 billion years, strontium 84, 86, 87, 88, yttrium 89, zirconium 90, 91, 92, 94, zirconium 96, 20 billion years, niobium 93, molybdenum 92, 94, 95, 96, 97, 98, 100, 7 billion years, technetium 97, 4.21 million years, right? That's synthetic. Technetium 98, 4.2 million years. That's also synthetic. Technetium 99, 211,000 years. That is not synthetic. That's trace amounts of that naturally. But that's the one that I would get, that I got. I don't have those two. Ruthenium 96. Let me get a chair real quick. Ruthenium 96, 98, 99, 100, 101, 102, 104, rhodium 103. Okay. Palladium 102, 104, 105, 106, 108, 110. Silver 107, 109, cadmium 106, 108, 110, 111, 112, 113, 8 million billion years, cadmium 114, cadmium 116, 28 billion years. Rocky coming. Okay, where was I at? Cadmium 106, 108, 110, 111, 112, 113, 8 million billion years. 114, 116, 28 billion years. Indium 113, Indium 115, 441,000 billion years. 10, 112, 114, 115, 116, 117, 118, 119, 120, 122, 124. Antimony 121, 123. Tellurium 120, 122, 123. 124, 125, 126, 128, 2.2 million billion years. That's the longest radioisotope that we know of. Tellurium 130, 820 billion years. That's also very long. Iodine, actually, it's not the longest, but that's pretty long. Iodine 127, xenon 124, 18,000 billion years, right? Okay, and then you get xenon 126, 128, 129, 130, 131, 132, 134. Xenon 136, 2.16 thousand billion years. Right? Cesium 133, barium 130. This is a range here. I would prefer a value, and I looked it up. It was 1.6 thousand billion years for barium 130. I think it was on Wikipedia or somewhere. But barium 132 is stable. 134, 135, 136, 137, 138. Lanthanum 138, 102 billion years. That's still very long, so. Lanthanum 130. Lanthanum 139, let's see, cerium 136. Cerium 138, 140, 142, praseodymium 141, neodymium 142, 143, 144 is 2.29 million billion years. Neodymium 145, 146, 148. Neodymium 150, 9.3 billion years. Okay. Another one that has no stable isotopes, promethium 145, 17.7 years. That's synthetic. Promethium 146, 5.53 years. That's synthetic. We have promethium 147, 2.6 years. This one does occur naturally in uranium ore, which that's what I'm counting on because I bought my sample off eBay like an idiot. So I don't have a verified. Well, it could still be promethium, but I need to have more confidence in that, honestly. But let's see, 2.6 years. Yeah, this is for one's collection purposes. This is the one that's the most difficult to collect. I mean, polonium, you can get the lead needle, so that's not an issue. So promethium is just so short-lived. It's hard to collect. It really is. But that's why it's the last one that I'm on right now. I just need to watch him to deliver, and then I'll explain later. Samarium 144, 146, 103 million years. This is just trace. I just wanted to include this because this is over 100 million year half-life, which is quite long. That's pretty, if you could find something to do, if you could find something useful, if you needed something that had this amount of radiation specifically, then that would be useful. But I don't think it would be other than that. But Samarium 147, 107 billion years. That's a big jump there. And then Samarium 148, 6.3 million billion years. That's another order of magnitude more stable. Not like the million billion years, though. That's just fucking, can you not just be stable? Like, Tellurium back here. Tellurium. What are you doing? Okay. But, yeah, Samarium 149, 150, 152, and 154 are the actual stable ones, other than 144 down here, which is stable. I don't know what the difference is between observationally stable. Well, I know what the difference is between observationally stable, which is it's never been observed to decay. That's observationally stable. And actually stable. Like, what's the difference? Like, can we just assume that something's stable? I don't know. Europium 151, 4.62 billion years. Europium 153 is stable. So, I don't know what the percentages are. Actually, I got them over here. I don't even need to... Just go to Europium. Let's look at it real quick. It's 47% of this radioactive one here. And then 52% of the stable one. Oh, this is... I like how this is presented, actually. I need another notebook. I really do. Ooh. Look at all these fucking isotopes, especially for lead. Holy shit. 214. Okay, whatever. We continue to gadolinium 152, 108,000 billion years. And then basically, after that, you do gadolinium 154, 155, 156, 157, 158, and 160. Right? And then... I'm like, so there's this isotope, and then this other one. Terbium 159, dysprosium 156, 158, 160, 161, 162, 163, 164. Holmium 165, erbium 162, 164, 166, 167, 168, 170. Yeah. Thulium 169, 168, 170, 171, 172, 173, 174, 176. Right? And then... you have lutetium 175, lutetium 176. 37 billion years. That's the lowest one we're going to get for a while, actually. Until we get to, what is it? Well, excluding the trace ones, you have to go all the way until polonium, so. In terms of most stable isotopes of an element. Okay, hafnium 174, 70 million billion years. Hafnium 176, 177, 178, 179, 180. So you can see that the atom is verging up on 200 nucleons. It's still pretty stable. Tantalum 180M, so that's metastable. There is an M there. Yes, I just said M. Tantalum 181. So this one's observationally stable, but we suspect that it's radioactive, I think, because literally every other metastable is. But we have tungsten 181, tungsten 180, 1.8 billion years. That's quite a long time. That's actually, yeah, that's very long. For this page it is. Tungsten 182, 183. 184, 186. Okay. Oh, yeah, this page is the entire D block. Cool. Rhenium 185. Rhenium 187, 41.2 billion years. Osmium 184, 11.2 thousand billion years. Osmium 186, 2 million billion years. Osmium 187, 188, 189, 190, 192. Iridium 191, 193, platinum 190, 483 billion years. Platinum 192, platinum 194, 195, 196, 198. Gold 197. Mercury 196, 198, 199, 200. Yeah, Mercury, good job. I mean, gold could get there, but it would be radioactive. So, I mean, actually, pretty much any of the, well, I don't know, but yeah. We finally hit the 200 mark. Mercury 200, 201, 202, and 204. Those are all stable. It's a lot of nucleons. Holy shit. But, yeah, they're like, they all just fit together like puzzle pieces or something. Thallium 203 and 205 are stable. Lead 204, 206, 207, and 208 are stable. And those are the last stable elements. Stable. Those are the last, well, these two are. Those are the last stable isotopes. And the four biggest of them would be, or the three out of the five biggest of them would be lead. Actually, four out of the five biggest would be lead. But the first three would be all lead. So lead. You can see it's the last stable element because of lead 208 here. Because everything after this is all black, as you can see here. Same with all this and all this and all this and all this. The seventh period. That's all the seventh period is long. But just like the sixth. So lead 209, trace amounts 3.2 hours. Trace lead 210, 22.2 years. This is the one that beta decays into bismuth 210. And then into polonium 210, which is how I get polonium into my collection. In very small amounts, but it's there, it's there, it's there. You can measure it. You can fucking do it. Just do it. Bismuth 209, 20.1 billion years. Okay, let me get you some bismuth real quick. Some bismuth. It looks pretty stable, right? 20.1 billion year half-life. It's like, it's so, it doesn't ring a bell as radioactive, but it is. Something that weakly radioactive, but that's the biggest one we're gonna see for the rest of the periodic table. Bismuth 210 has a half-life of 5 days. It's a trace number. We have synthetic polonium 209, 124 years. That's the longest one we could get. But the natural one, trace 210, 138 days. I think that's the only naturally, well, it's not the only naturally occurring. There's polonium from decay chains of uranium, but the main way I think that it comes about is from this lead 210 here. The beta decaying that I was talking about through bismuth here. Acetine, 3 synthetic isotopes here up here. Astatine 209, 5.4 hours. Astatine 210, 8.1 hours. And astatine 211, 7.2 hours. But the trace ones, astatine 218, 1.27 seconds. This is the one that I got. And like, we'll get to how many atoms. 1.27 seconds. Astatine 219, 56 seconds trace. So I'd have a total of around 1,300 atoms of astatine. Which is not a lot. You can't see that shit. So we couldn't tell you what it looks like. And it's spread across the entirety of a huge chunk of ore, so you couldn't isolate it. You wouldn't have enough time to isolate it because look at these half-lives. 1 second and 56 seconds. Can you fucking do an entire chemistry session in 1 second? No, you don't. So then you have to rely on the uranium ore. You have to rely on the fact that it's not pure. It's been decaying for billions of years. Possibly. I don't know. Well, yeah, it has. Yeah, it's a natural ore. It's not been disturbed until humanity found it. So it's very impure from its decay products. But radon, yeah, these are the ones that I would have. Not very many atoms of it. But radon 222, 3.82 days, trace. Trace francium 223, 22 minutes. Again, got that from decay chains and stuff. Trace radium 226, 1.6 thousand years. Trace actinium 227, 21.7 years. Trace thorium 229, 7.9 thousand years. That's decently long. Thorium 230, 75.4 thousand years. It's like a really small fraction of a percent of abundance, but it's there. It's like 0.002% or something like that. However, the vast majority is thorium-232, which has a half-life of 14 billion years. You can see it went up from the elements back here. It actually got more stable. When you have the right number, when you have the 90s amount of protons up until, 99 or, yeah, actually all the 90s are pretty stable. Except for 99 is kind of not that stable. And 80 and 91 would be the only exceptions. But actually, 91 is still pretty stable, yeah. Protactinium 231, 32.6 thousand years. That's about the only one that you can get. I mean, there's the decay products of uranium and stuff. However, I like to not even consider those if there's a better, like, more stable version that's even more common and natural. Like this one. This is longer lived, so I probably should have included the other ones. What was it? 230 and 234. But trace, I'm not going to say all these. Maybe I will. But the main ones are 234, 245,000 years. Yeah, we'll not skip over this. 233, 159,000 years. 235, 704 million years. So I actually got I calculated the amount of grams I have in my 330 gram uranium ore sample. I would have roughly 15 to 20 grams. I calculated at 18 grams of 235. It's obviously mixed throughout the sample, so you'd have to isolate it with, I don't ask the government how to do that, because I don't know how to do that. But I think that's why they purposely keep it out of the hands of citizens or something. Or maybe it's perfectly legal to isolate uranium-235. Who knows? It's perfectly legal to buy ore. So, I mean, what's the difference? I buy the ore, I isolate it. Especially if it's just for a collection. Like people need to chill the hell out. Trace uranium-236, 23.4 million years. So yeah, 15 to 20 grams of that per 330 grams. So that's around, 0.7%, something like that. I didn't calculate that. I just fucking know the abundance of this one. Uranium-238, 4.46 billion years. Wow. That rivals this one here in the billions of years. And now, after uranium-238, that big billions of years, it's going to suddenly drop off from here. And in every couple elements, it's going to drop off by a order of magnitude. The half-lives are going to fall. They're going to drop. Okay, so Neptunium-237, 2.14 million years. So I got some of that as well. I mean, I can tell you several places I got it. The americium source from the smoke detector, and because that's what the americium decays directly into. This one, 241 to this one, 237 neptunium, americium 241 beta or alpha decay. I also got it from uranium ore. There's a small amount of that in there. You'd have to look it up how much exactly. It's like, I don't know. But that's pretty long, 2 million years. Trace plutonium-238, 87.7 years. This is the one that I got. Trace 239, 24.1 thousand years. I also got some of that. 240. And if I had any of these other ones, it would be like in small amounts in the uranium ore. Like, again, trace. Based on the number of atoms, I'm just going to call it all trace if it's not uranium in the uranium ore. Because the 235 and 238, I'll just call that uranium ore, everything else trace. Okay, good. Even if it's like a gram or something, whatever, who cares? I don't think there would be a gram of anything else in there. Even actinium. If it's been decaying for billions of years and how not radioactive uranium is, it's not going to have grams in there. Plutonium-240, 6.5 thousand years. So it gets significantly more stable, than 238. And then, yes, plutonium-242, 375,000 years. This one's synthetic, but still. And then 244, 80 million years. 80 point something. I forgot they updated it. But, so it's got a lot more stable than the early part here, which I have. Wish I had some of this, man. Give me some of this. Because 87 years ain't cutting it. It ain't cutting the radioisotope game. If I had that would be great. This one. Actually, I probably do in the uranium ore. But now everything past this is synthetic. Because that's the extent of the uranium ore that it can get up to in trace amounts. That's what this trace means. Trace and trace. I got that straight from Wikipedia. So argue with them if you don't fucking like it. Americium-241, 432 years. That's the one that I got. But we have Americium-242 metastable 1, which I think is different from 242 metastable. I'm not sure the exact differences. Let me not get into the ideas of it, though. 141 years. 243 is 7.35 thousand years, so that's the longest lived one. Curium, 8 synthetic isotopes here we have. I still got it. Curium-242, 162.8 days. Curium-243, 29.1 years. The reason I brought those up is because I have those. Curium-244, 18.11 years. So those 3 I got. These other ones I probably having from neutron capture in small amounts. Significantly less than these other ones. Maybe tens of thousands, millions of atoms. But these... I have several hundred billion atoms of 243 and 244, and maybe a billion or 2 billion, somewhere around 5 billion. But it's rapidly decaying for the 242, so if it was 5 billion, then it's now not 5 billion anymore. It's now something like a few hundred million, maybe at worst, you know. But still, it'll keep going down. But these ones will last significantly longer. In another 15 years, you'll still have half of your Curium-244. So it's, you know, a long time. Curium-245, 8.25 thousand years. So out of nowhere, and then I don't have that in my collection. I'm not complaining or anything, but why is it so hard to make these? What's the difference? It's so much harder to make, but it's so much more stable. You can't get it out of there in time before it neutron captures into a bigger one, probably. How do you get these? How do you get me some 247, man. 246, 4.76 thousand years. That's still a long time. That's way more than these three up here. 247, 15.6 million years. This is the biggest one we're going to see. Another peak. Actually, this is actually the final peak in the millions of years. The previous one was, the final peak in billions of years was uranium. The final peak in millions of years is curium here. So you're not going to see another million-year half-life for the rest of these. Curium-248, 348,000 years. Curium-250, 8.3 thousand years. Berkelium-247, 1.38 thousand years. We got Berkelium-248, more than 300 years. Thanks for that. But it could be 500 and it would still be valid, but, you know, it's not very specific. Berkelium-249, 330 days. This is the one that I got here from the neutron capture. Well, would you not have this one, though? Wait. I'm assuming it gets up to Curium-249 by neutron capture, right? Then it beta decays into Berkelium-249. But if it got up to 249, couldn't some of the... Oh, this doesn't beta decay as much, so you wouldn't get this often. You wouldn't get this one often, but you would get 249 often. Oh, because it decays more. So you'd probably get this one more. So the more radioactive ones bring about the other isotopes. Oh, that's probably why they selected these curium ones here. They probably did that on purpose, didn't they? They're not as stable, right? Or even if it is, well, they bring it, the more radioactive they bring about. Well, no, you could still have these ones. They neutron capture up to, well, if you had the ability, neutron capture up to 249. Then that beta decays into 249 here, Berkelium-249, 330 days. Then that beta decays into Californium-249, 351 years. And then you also have Californium-250, 13 years. So the 249 is the one that I got. Californium-251, 898 years. Damn. It's not going to be even close to 1,000 years for the rest. It's just dropping off, like off a cliff. This is where all the long-lived ones end, at Einsteinium. They actually end in California. Damn you, California. You had to get it, the last one. Basically, the last one with a half-life longer than... An isotope with a half-life longer than humans typically live, which would be these two here. We live longer than a year, so that's why I can say this is less, and everything after. Einsteinium-252, 1.29 years. Einsteinium-253, 20.4 days. I still got that motherfucker in, like, a small amount. A few hundred atoms, probably. And then a few hundred atoms of Einsteinium-254, 275.7 days. A total of around 1,000 Einsteinium atoms is in my collection. So that and astatine would be the smallest samples I have in my collection in terms of mass. Like, for the radioactive ones, you kind of have to do that. Because, well, some of them are incredibly rare and hard to get, and some of them you have to rely on decay chains, like astatine. And you do have to rely on decay chains with Einsteinium, too. I think the only one in the element cube that doesn't rely on decay chains is curium here. The one in the element cube that I have, I would show it, but it's in my safe. Okay, now we're on to elements that I don't have in my collection, so I'm no longer gonna fucking make the video any longer. But fermium-257, 100.5 days. Mendelevium-258, 51.5 days. Mendelevium-260, 31.8 days. Nobelium-259, 58 minutes. Okay, so there officially goes the collectible elements. Fermium and Mendelevium, which sound collectible to me, 31 days. That sounds like a long enough time to synthesize it and sell it. A 31-day half-life. Sure, it might be rapidly deteriorating, but you can still collect it for a short enough time to make a video about it, probably. However, Nobelium, that's not long enough. 58 minutes, we're done. We just died. Our element collection dies right there. Even Bill Gates' collection dies there. Bill Gates, he's like, let me get some fermium and mendelevium or whatever. You give me, here's $400 trillion, whatever. Who cares? But nobelium, I can't get that shit. But lawrencium-262, 4 hours. Lawrencium-264, 4.8 hours. How do you even get it? You can't even get it long enough to ship it somewhere. You're like, okay, we gotta wait till tomorrow. Oh, we can't because it decays in 4 hours, so we have to get it. You can by the time it arrives. Well, you didn't even get to the destination in 4 hours, so. But lawrencium-266, 11 hours. We'll be generous. We'll give you 11 hours to deliver the package. No, we'll be even more generous. Rutherfordium-263, 15 minutes. You got 15 minutes to deliver. Actually, we're going to give you the element as soon as we synthesize it. So you got to be ready to deliver it. As soon as we synthesize it, we'll give it to you. And then you have to arrive there in less than 15 minutes. It has to be less than 15 minutes. Can't be a dot over. And then you sign it over to the person, right? They give their signature for $11.3 billion or whatever to get the Rutherfordium atom. And then, right as soon as they open it, it decays. And then, because it's been 15 minutes. But Rutherfordium-265, 1.1 minutes. Rutherfordium-267, 48 minutes. Dubnium-267, 1.4 hours. Dubnium-268, 16 hours. So that's, you're not going to see one that long in a while. Actually, ever after this. I mean, unless we go back to it, which we will. But Dubnium-270, 1 hour. Seaborgium-267, 9.8 minutes. Seaborgium-269, 14 minutes. Bohrium-270, 2.4 minutes. Bohrium-278, 11.5 minutes. Question mark. That's a question mark if you didn't know. I need more water. But the reason there's a question mark, I guess, is because it's not confirmed or something. I don't know. Hasium-271, 46 seconds. Hasium-277, metastable, 2.16 minutes. Meitnerium-278, that is 4 seconds. Meitnerium-282, 1.11 minutes, question mark. Tungstenium-281, 14 seconds. So it starts getting uncertain here, the precision of our... Well, it's not the precision of our scientific instruments. That's not the concern. The concern is how hard it is to make these. So I guess we don't have much study time, It's like, so we have to guess. We don't have enough information. We're not like, how do we know? But Dubstenium-281, 14 seconds. Rhenginium-282, 2 minutes. Rhenginium-283, 5.1 minutes, question mark. Rhenginium-286, 10.7 minutes, question mark. Wow. Oh, yeah, I'll tell you at the end, actually. We're almost done. Copernicium-285, 30 seconds. We have Nihonium-285, 2.1 seconds. Nihonium-286, 9.5 seconds. Nihonium-287, 5.5 seconds. Fluorovium-289, 2.1 seconds. Fluorovium-290, 19 seconds, question mark. Moscovium-288, 193 milliseconds. Moscovium-289, 250 milliseconds. Moscovium-290, 650 milliseconds. Livermorium-293, 70 milliseconds. Livermorium-293, 80 milliseconds. Tennessine-293, 25 milliseconds. Tennessine-294, 51 milliseconds. And Oganesson-294, 700 microseconds. That's supposed to be the micro symbol there. So if you want to talk about blocks that I got, right? The blocks that I got are 1s, 2s, 2p. So this is going to bother some chemists probably, or the people who study electrons, because I'm not talking about the Aufbau principle or the monologue rule, so chill. This is just block, block, and position, because I care more about the freaking isotopes than anything. So, but I use the blocks to measure out. I use it as like a ruler for the elements, because if you don't have the blocks, then it's just like a bunch of elements after a bunch of other elements, more elements, and then some elements, and then you got some elements. So I like it to divide everything, and then I like saying, oh, lithium, beryllium, the same, potassium, calcium's the same, sodium, magnesium's the same. That's cool and stuff. So I like that. But yeah, 1s, 2s, 2p, 3s, 3p, 4s, 4d. I know that they call that 3d or something, but I'm not going to get into it. 4d, 4p, 5s, 5d, that's still 5d, 5p, 6s, 6f, yeah, all that, 6d, all of 6p, yes, I do. All of 7s and the majority of 7f, not all of it though. Up to Einsteinium here, but not up to fermium and nobelium I don't have. So 11 out of 14, that's the majority. 78%, I already looked it up. So I didn't like fucking calculate it or something. I'm not that smart. But we have 7D, I don't have a single one, and 7P, I don't have a single one. Has nothing to do with the chemistry of those blocks at all. It has more to do with how the fact that this is 262 nucleons, and that's a lot. It's not very stable in any configuration. Or especially when it has 103 protons and then that configuration of whatever and all that stuff. I don't see another one here that's 262 though, so let me pick a better example. Like 267. You can't find a... There's 3 different ones here. Rutherfordium, dubnium, and seaborgium are all 267. But let's see. 48 minutes, 1.4 hours, and 9.8 minutes. So they vary, right? But they're all around the same, like an hour or so, or like 10 minutes or whatever. Who cares? I'm not saying who cares. Like, this is all interesting. I like this. But the part that I say who cares about is like... Actually, I don't know why I said who cares. I kind of just say that out of nowhere for no reason. But, let's see. Synthetic. Yeah, they're all synthetic, yeah. All these ones are, yeah. But, yeah, it's cool. I mean, California, my God, Einsteinium is crazy. Now, it's crazy. I mean, yeah. Now, I got some samples I can show. These are just the ones outside of the, these are just the ones outside of my safe. So I got like a display table. Well, first of all, you can see the copper is copper. You can see that the copper is copper. And you can feel and see that it's copper. And there's my doggo. Wait. There you go. You can see a blurry copper image of him. I gotta pee, man. I got the pee shiver. Yes, I did. Okay. Thanks for watching. Oh, not in focus. There we go.